Finally, this is a stream that I might not have to delete. Because before I was doing some coursework, maybe I was giving out too many hints. And, or I was just doing stuff that I couldn't really show. And so I wasn't talking much and the screen was blurred. There wasn't much to see. But now I'm just doing my thing and reading. So I hope this will just stay here. I'm not going to talk about me very much because I don't have much time today. Save that for another day. Okay, so I'm going to be reading this, not very carefully, just getting the main point. And maybe just like some background. I do want to say this is not my area of expertise, so I'm coming to this as an outsider, so sorry if I don't know something very common, it's common knowledge. Sorry if I don't understand something, sorry if my IQ is too low. Anyway, let's just get started. So here's the abstract. Deep learning algorithms are well known to have a propensity for fitting the training data very well and often fit even outliers and mislabeled data points. That is true. Such fitting requires memorization of training data labels requires memorizing the mapping between the training data and their labels. A phenomenon that has attracted significant research interest but has not been given a compelling explanation so far. Hold on. Okay. A recent work of Feldman, this author here, proposes a theoretical explanation for this phenomenon based on a combination of two insights. Okay, maybe I'll look at that later. First, natural image and data distributions. What other things besides images are informally known to be long-tailed, that is to have a significant fraction of rare and atypical examples. Okay, so let's say if you project the data set somehow, or maybe you just don't, and maybe cluster them by class. I'm assuming these are like classification data sets, but not necessarily. You may see a cluster per class. And this tail is the examples that are far from the mean of that cluster, or the centroid of that cluster. So they're saying that these sort of natural data sets that aren't just like generated, they have many examples that are far from that centroid. Second, in a simple theoretical model such as such memorization is necessary. I'll trust them on that since they're speaking so boldly for achieving close to optimal generalization error when the data distribution is long-tailed. Generalization error. I'm thinking something like validation accuracy. However, no direct empirical evidence for this explanation or even an approach for obtaining such evidence were given. Maybe this is what this paper is about. Influence estimation, right? In this work, we design experiments to test the key ideas of this theory. The experiments require estimation of the influence of each training example on the accuracy at each test example. They say at here and of here. Yeah, I guess that's fine. On each test example, I don't know. As well as memorization values of training examples. So there's the influence of the training example on a test example, as well as the memorization of that training example. They're gonna give me ways of quantifying such things. Estimating these quantities directly is computationally prohibitive, but we show that closely related subsampled influence and memorization values can be estimated much more efficiently. So I'm guessing there is a dumb way to do this. Maybe we can think of some ways immediately, but they're saying that's very dumb, that's expensive. So they're gonna give us a way to do that cheaply, of estimating that cheaply. Maybe not do it, but estimate it. Our experiments demonstrate that the significant benefits of memorization for generalization. Oh, demonstrate the benefits of memorization for generalization on several standard benchmarks. Our experiments also provide quantitative and visually compelling evidence for the theory put forth in here. Let's take a quick peek at this. Does learning require memorization? Wait. Let's take a look. Stated our results on image recognition tasks. So this is an explanation and theoretical model for this sort of memorization thing. The cost of limiting memorization in learning. And explain the difference. So this perhaps shows us and explains that memorization is necessary. Okay. Let's read the intro. Perhaps the most captivating aspect of deep learning algorithms is their ability to generalize to unseen data. Yeah, I like them because of that. The models used in deep learning are typically overparameterized, making it easy to perfectly fit the training data set without any generalization. Yes, in fact, the standard training algorithms do fit the training data very well, typically achieving 95 to 100% accuracy, even when the accuracy on the test data set is much more modest. Yeah, so that's overfitting. I don't know why we still talk about this, but it's like even the dumbest thing can get very high training accuracy. We usually don't care about that as much as validation accuracy. In particular, they usually fit obvious outliers, such as images with no discernible features of their class, and mislabeled examples. The only way for a training algorithm to fit an example whose label cannot be predicted based on the rest of the data set is to memorize the label. Yes. So if it's like mislabeled, then you can't do anything but memorize it. What is this? This notion of label memorization is defined rigorously. Okay. Further, it is now well known that standard deep learning algorithms achieve high training accuracy even on large and randomly labeled data sets. It is now well known. It was well known before. Understanding deep learning requires rethinking journalism. Oh. I think I remember seeing this somewhere, and it was like controversial, right? Yeah. Hmm. I think I maybe read this or read an abstract. Yeah, I definitely read this abstract. And I thought we kind of already knew this. So we don't need to rethink anything. We just know that if you have enough parameters, your parameters can memorize the training data set. Uh, Especially when the number of parameters is greater than or equal to the number of training examples. Maybe I'm missing something. Oh, he's the first author. Okay. Hmm. Uh, anyway, this propensity for label memorization is not explained by the standard approach to understanding generalization. Okay. At a high level, the standard approach upper bounds the generalization error, probably like validation error, by the sum of an upper bound on the generalization gap controlled by a model complexity or stability parameter and the empirical error. This thing, I don't understand what this is. Maybe this is like a hyperparameter, the complexity parameter, like depth or number of parameters, number of non-zero parameters, let's say. I'll just leave it. Fitting of outliers and mislabeled examples does not improve the generalization error. Sure. Therefore, to avoid overfitting, the balance between the complexity parameter and the empirical error is supposed to be tuned in a way that prevents label memorization. Memorization is generally thought of and taught in ML courses as being the opposite of generalization. I don't know whether it's taught. Maybe it was taught and I just forgot. We just think of generalization and overfitting as the opposite of that. This disconnect between the classical theory and modern practice was highlighted in the work of the first author and a bunch of others. Okay, this thing, and generated a large wave of research interest in the topic of generalization for deep learning. I mean, I don't know if it generated. There was always a bunch of interest in, like, this is why deep learning is attractive. Okay, I'll leave it. The bulk of this research focuses on finding new ways to control the generalization gap, or showing that training algorithms induce a form of implicit recursion. And again, like, this is not, like, my background is on totally different things, not even computer science. So I'm sorry if I don't know something that's very well known. Okay. I'm kind of skimming now. A recent work of this other author, no, this is the first author, proposes a new explanation for the benefits of memorization. Fine. And here, the need for memorization and statistical indistinguishability of useful from useless examples are theoretically demonstrated using an abstract model. So yeah, it's hard to distinguish between something useless like a mislabeled example or an example that is like just highly atypical. while it has been recognized in many contexts that modern datasets are long-tailed, it is unclear whether this has any relationship to memorization by modern deep learning algorithms, and if so, how significant is the effect? Okay. How are we doing on time? Spent 15 minutes. In this work, we develop approaches for empirically validating the long tail theory. Okay, wait, I have to read this. Useful examples from the long tail, in the sense that memorizing them improves the generalization error, can be statistically indistinguishable from a useless one. Yeah, that's what I said before, such as outliers and mislabeled ones. Cool. This makes memorization of useless examples necessary for achieving close to optimal generalization error. And this is the long tail theory. I see. So we validate this long tail theory. Starting point for such validation is examining which training examples are memorized and what is the utility of all the memorized examples as a whole. To make it more concrete, we recall the definition of label memorization from here. So this was established before. For training algorithm A, operating on a dataset S, which is a tuple of tuples of, I'm guessing, examples and their labels of size n, the amount of label memorization by the algorithm on a particular example in the dataset is defined as this thing. The probability for the result of this algorithm, this training algorithm on the data set. Maybe this is a hypothesis. Yeah, probably. Probability that the hypothesis, which gives you a label, I'm guessing, is the correct label. So what is this? This is the training accuracy. Yes. Minus the training accuracy without that example. Yeah, where this denotes the data set with that particular example removed. So, can you imagine this being negative? Like if this example were just something adversarial, let's say, learning it would decrease your training accuracy. I don't know. I'm just making shit up here. But for now, I can imagine such an example. You train on it and you have a certain accuracy, but it's not helping. You leave it out, you just forget about it, let's say. And then your training accuracy is higher, and then your memorization is negative. Possibly. Maybe we can look at their plots later. So this captures and quantifies the intuition that an algorithm memorizes the label if its prediction on this example based on the rest of the dataset changes significantly once this example is added to the dataset. The primary issue with this definition is that estimating memorization values with standard deviation of sigma requires running the algorithm without that example on the order of 1 over sigma squared times for every example. So it's like n over sigma squared. So if you want a small sigma squared, what you do, this is like the estimation of memorization, which is like the same unit as accuracy. So you want it to be pretty small. You want this sigma squared to be pretty small. Yeah. So here's an example. To achieve sigma of 0.1 on a data set with 50,000 examples like MNIST. So that's not even that low. You need to train like whatever 50,000 over 0.1 squared is. Let's add some zeros to this. We bypass this problem by proposing a closely related estimator that looks at the expected memorization of the label of xi, so yi, on a random subset of S that includes m less than or equal to n of examples. Maybe not of. It can be seen as this thing smoothed by the random subsampling of the data set and is also related to the Shapley value of I for accuracy on itself. What's this? Something I should know? Let me look it up real quick. It's solution concept theory. Gain from the cooperation. Perhaps this is related to Nash equilibrium. I may have seen this before and I just forgot. Okay, that's fine. Most importantly, for m bounded away from n and 1, this memorization value can be estimated with standard deviation sigma for every I, for every example at the same time using just O of 1 over sigma squared training runs. What is this? For m bounded away from n, so m cannot get too close to n, and 1 cannot be 1. So it's basically for m far from n and 1, not n and not 1, if you want to be very careful. We compute memorization value estimates on MNIST, CFAR 100, and ImageNet. Then estimate the marginal effect on memorized examples on the test accuracy by removing those examples from the training dataset. So instead of this, they'll have some kind of like expected difference in training accuracy. That's the memorization. We find that aside from the MNIST dataset, a significant fraction of examples have large memorization estimates. The marginal utility for the memorized examples is also significant, in fact higher than a random set of examples of the same size. So MNIST is weird. What is this to? Yeah, okay, they're including MNIST just to compare. Memorization plays a much smaller role. When the variability of the data is low, corresponding to a low number of subpopulations in a mixture model. And the number of examples per class is high. Yeah, so we got 10 classes, and I believe it's balanced. So we got like 5,000 examples. Yeah, 5,000 examples per class. And what are they? They're just handwritten images of handwritten digits. How variable could they be, really? I mean, maybe some people's handwriting really sucks. So, but they're still recognizable as handwriting. Okay. More important prediction of the theory is that memorization is necessary since each memorized representative of a rare subpopulation significantly increases the prediction accuracy on its subpopulation. Yeah. If we have a rare subpopulation, not very many examples in that class, then the importance, let's say, of each one of them is higher. We observe that this prediction implies that there should exist a substantial number of memorized training examples, each of which significantly increases the accuracy on an example in the test set. Okay. Further of the test examples that are influenced significantly, most are influenced significantly only by a single training example. So this is like empirical evidence that memorization really increases your test accuracy. The uniqueness is important since, according to the theoretical results, such unique representatives of a subpopulation are the ones that are hard to distinguish from outliers and mislabeled examples. This is a good point, good analysis. To find such high influence pairs of examples. So these pairs are like pairs of training example and test example. We need to estimate the influence of each training example on the accuracy at each test example. Now, if you do this in a dumb way, you're gonna do like 50,000 by 10,000 by 10. Wait, yeah, 50,000 by 10,000, let's say MNIST training runs. So this is the influence. It is the, what is this? Test example. It is the test accuracy with the whole training data set minus the test accuracy with that particular example left out. As with memorization values, estimating the influence values for all pairs of examples is clearly not computationally feasible. Yes. Famous proxy for the classical leave one, I'm assuming it's leave one out influence is the influence function. What's this? Koken-Weiss, whatever. Residuals and influence in regression. I did not read this. Who proposed a method based on assumptions of first and second order optimality. Fine, I don't understand that sentence. Alternative proxies for measuring influence have been studied there. We propose and use a new estimator. Okay, so this is the new part. for influence based on the same subsampling as our memorization value estimator. Its primary advantages are that it is a natural smooth version. And they demonstrate, okay, it's cheaper. That's the point I got. What is this? We then locate all pairs such that our influence and memorization value of this is sufficiently large. Sufficient, they just choose a number. They justify this later. Overall, we found a substantial number of such pairs in CFAR 100 and in ImageNet. For example, we found these many pairs satisfying these criteria in ImageNet. Is that a lot? Yeah, that is. In these pairs, there were these many test examples. Yeah, that's like 3% of the test set, of which these many are influenced significantly by only a single training example. Okay, so these experiments support this long tail theory that you need to memorize some stuff. What is this? Related questions. While the architecture definitely plays a role, there are strong correlations between sets of memorized examples and high influence pairs for different architectures. Maybe we'll take a look at this later. Finally, as our influence and memorization estimators are still very computationally intensive, we consider a faster way to compute these values. Is it still intensive? Perhaps it's like something like training normally, right? Maybe it's like some quadratic thing on training normally. I don't know. I'll have to think about it. Specifically, instead of training the entire network on each random subset of S, we train only the last layer over the representation given by the penultimate layer of the network, trained once on the entire dataset. Okay. So it's like you have this pre-trained thing and you just freeze that. And you maybe estimate you basically do what they just said, but on only the last layer. I don't know whether that works. It's more efficient, but it fails completely at detecting memorized examples and gives much worse influence estimate. Yeah, that is pretty much expected. In addition to being a useful negative result, this experiment provides remarkable evidence that most of the memorization effectively happens in the deep representation and not in the last layer. Why did you even consider this then? Maybe this was proposed somewhere. Maybe they need to cite something. I'm skipping this related word. They're just taking a bow to everybody who they read. Okay. Here is something I want to read carefully. We're okay on time. Memorization and influence estimators. Our goal is to measure the label memorization by an algorithm A on a training dataset S and example I. Equation 1, we read it before. And the influence of a training example on a test example J. Both of these values are a special case of measuring the influence of a particular example, maybe a training example, on the expected accuracy at some example Z. Could be train or test. Or it is the difference between the accuracy the difference between the accuracy of that example minus the accuracy while trained without some example. Clearly the memorization, mem, is the influence. Okay. The memorization of example I is the influence of I on itself. Okay. As discussed in section 1.1, directly estimating the influence is expensive, so we propose a closely related influence value that looks at the expected influence of an example relative to a dataset that includes a random subset of S of size M that was bounded. More formally, for a set of indices, I, a subset of this thing, it is 1 through N. Okay, I've never seen this before. Let Si be a set. Si is the training set, okay? B, the data set consisting of examples from S with indices and I for a set of indices J, a subset of N. Let P, J, M denote the uniform distribution over all subsets of J of size M. Okay, subsets of size M. P is like, okay, it's a distribution over. Okay, so this is like what you get when you say iter-tools combinations in Python, and you set the subset size to M, and draw it from 1 through N, like iter-tools combinations range N of size M. Then we define this Z. We saw Z before. It's just some example. It is the expected influence of the train set and that particular example I on Z for I, or maybe this, yeah, it's not the train set, it's just some subset of the train set without that particular example of size M minus 1. Why M minus 1? Could be something to do with the variance. I'm sure they're gonna prove it somewhere, so I'm fine with that. Where by sampling a random subset of size M minus 1 that excludes index I, we ensure that the train set and that particular one. Okay, so it's like, Now, let's leave it. Is uniform over all subsets of size M that include the index I. We now show that subsampled influence values can be estimated with standard deviation sigma by training just some constant times 1 over sigma squared models. Skipping this. Okay. So we got a train set S, test set S test. These have primes. N prime is the size of the test set, huh? Learning algorithm A, subset size M, number of trials T. Sample T random subsets of 1 through N of size M. So I's are these subsets of indices. For K and 1 to T, number of trials, that's a hyperparameter. Train the model H. Okay, so that's a hypothesis. HK by running the algorithm on S. This is the training data set T. What is this capital T? Maybe time step or epoch? I don't think they said capital T before. Okay, well, let's keep reading anyway. So for T times, you train this thing on a subset. So is this looks like the typical thing you might do with just a mini batch, but this is not a mini batch because it's sampled with replacement. Okay. Then for I in 1 to N, huh? You calculate this thing. The memorization is the... What is this? This is the training accuracy with and with. So it's the difference between the training accuracy with and without that particular example, I. So this I is like the one you leave out over here. And then for J, you leave out I for J in 1 to N prime. So J corresponds to test example indices. It is a test example index. The influence, this influence M is the test accuracy within. So it's the difference between test accuracy with and without that particular example. And all this is cheap because it's not training. It's just like you've trained it. This is, yeah, so the tricky part is not using your typical mini batches here, but sampling with replacement. And you return the memorization and influence. So this is like a table. So for MNIS, this is like a 50,000 by 10,000 table you have. The larger the subset size parameter M, the closer is our estimator to the original influence. Then why not just make it N? That is because, wait. Why is my brain not working? T, do it T times. Oh, because this is expensive. No? I don't know. To roughly balance these requirements in all our experiments, we chose m equals 0.7 of n. I would think maybe you would choose 0.5 to begin with. Just like a gut feeling kind of thing. Due to computational constraints, we chose the number of trials to be t equals 2000. So like 2000 mini batches, let's say. Not really mini batches. 2000 samples. Yeah. For ImageNet and 4000 for MNIST and C400. We remarked that for m equals n over 2, okay, that was what I was thinking earlier, our influence value is closely related to the Shapley value of example I for the function that measures the expected accuracy of the model on point Z. Okay. The Shapley value is equal to the expected marginal utility of example I relative to the random and uniform subset of all examples. Oh. I don't know why you chose 0.7 then. Maybe they explain it somewhere. We chose this. No, that's different. Okay, so the result now. I'm done reading. Let's just look at some plots. Examples of memorization values from ImageNet, Bobsled, and C400 Class B. Okay, I know this is hard to see, but let's, if we look at one, these things, like these are hard to tell are bobsleds. Like you look at this, what is this? You would say maybe, I don't know, but you wouldn't say this is a bobsled. There's very little in here besides this track and then these little bobsleds that would say this is labeled bobsled. And these are more typical examples. And this is easier to interpret. These are very typical handwritten digits. These are harder. And these, yeah, you can say this is a 2. What is this? This is a gamma. Of course, there's no gamma class. What is this? 7 with some across. This looks like an 8. Delta or whatever. This looks like a 0, right? You could even say this is mislabeled. 6, I'm guessing. Yeah, 6. And then these are B's. Effect on the test set accuracy of removing examples with memorization value estimate above a given threshold and the same number of randomly chosen examples. Fraction of the training set remaining after removal is in the bottom plots. Okay, so these are aligned. Shaded area in the accuracy represents one standard deviation on 105 trials. Okay. So this is the test set accuracy from removing that memorized one. Oh, all of those whose memorization is above a certain threshold, and then the resulting accuracy. So, it's a better estimate. Wait, how do I interpret this? So intuitively, if you remove the memorized examples, you avoid memorizing, your accuracy decreases. If you remove a random example, it's more likely to be a useless one. So when these are close, when these are far, then you have identified a bunch of examples that are not necessary to memorize. Wait, that are necessary to memorize. Yeah. I don't see any shaded area here. Maybe it's so small that it's not showing up, which means that your estimate is very good. A standard deviation accuracy on 100. Okay, so not your estimate. This is like just your experiment variability, which is good. Like, this is already going the extra mile, doing multiple runs and showing how things vary. Histogram of the influence estimates for all the pairs from the ImageNet, the 400 and MNIST datasets that were selected according to algorithm 1 and criteria described in section 2. So the frequency of examples with influence above a certain threshold. Oh, influence in a certain bin. So we see on ImageNet, we got some, I don't know, some typical looking natural histogram. CFAR 100, maybe we have more atypical examples. MNIST is very, there's not much variability in MNIST, so this, I believe. Anything else we can look at? Examples of influence estimates for memorized examples from MNIST. Left column is the memorized examples. Okay. And their memorization estimates above. Okay. For each training example, 4 most influenced examples in the test set are given together with the influence estimates. So I like this, just like to illustrate how much some training example influences some test examples. And here's the class label. This is a 5. And it totally looks like a 3. So this was very influenced. Yeah. So there's this one stroke that's going like kind of in the middle of this one. This is a 3. So this collapsed upper part influenced these. Not so much these. I didn't expect this one though. These, it's like kind of the same idea. Maybe it's because this one's thicker. Okay, done staring at this. Additional examples of influence estimates for memorized examples from CFAR 100. Format as in figure 4. Hmm. Worm, squirrel, crab. Yeah, I'm not gonna look at these natural images. Rain barrel. This is ImageNet, right? Rain barrel, huh? So this is a very atypical looking one. Yeah, sorry my colors are inverted. I'm kind of used to it now. This is like a black barrel with some stuff tied on it. This looks like the same thing. Could even be the same barrel, just taken from a different angle. So this is the next highest influenced example. Carpenter's kit. Okay. Okay, so this is obviously the same dam. Coffee pot. Like if you just flip this horizontally, it kind of looks like this. Yeah, this part is very distinct. And then here's a crane. Okay. What is this? Does the last layer suffice for memorization? They said it doesn't. But let's think about this. Yeah. What intuition, though? Whose idea was it? The intuition is that if label memorization mostly happens at the final layer, then we could derive similar influence estimates much faster. But why would you think that? They didn't cite anyone as far as I can see. Well, let's just think of a simple example like if you have a weird example, which layers have to deal with it? It's all the layers. So the earlier you don't want to waste opportunity to deal with that example. So if the earlier layers don't deal with it, then the later ones have to, in addition to dealing with all of the more typical examples. So, can I draw? Sorry. You got, let's say a weird example activates something very much here. You want to deal with it right here. Because later, I know this is like a really dumb example, but like later, this one has to deal with not only this, but like all this other stuff mixed up. So if you didn't deal with it here, you're gonna have a more complicated problem here. So I don't find this intuitive. But maybe this was proposed somewhere and this is like a popular idea that I just don't know because I'm an outsider. Okay, what's this? Consistency of the estimation of memorization and influence across different architectures. Okay, so these are ResNet 50, 18, Inception, and DenseNet 100. What are these numbers? Consistency of the influence estimation. I don't know what Jacquard similarity is. Oh, maybe they were talking about it before. Average estimation difference. I can intuitively understand that. So what is this? Lower is better. So over here, it's like a similarity, so higher is better. So ResNet 50. These are more sophisticated. Inception. Did I? Kind of forgot what Inception was. It's like, okay, I'll leave it. What's this? Consistency of the estimation of influence between ResNet 50 and linear models trained on the penultimate layer representations computed on the entire CIFAR 100. So this was what we were talking about earlier. Yeah, not sure what to think of those. Here's the discussion. I'm going to skip this and references. Okay. They also have code. Let's take a few minutes and look at their code just to confirm what we read. So this is an MNIST example. I'm guessing they're using this JAX. Where's TensorFlow? Here, no? Maybe it was inconvenient to use TensorFlow. Batch correctness. What? Okay, where's your main? NPZFN is this string here? So they're loading some estimates into this tensor here, NumPy array. Okay, so this is like if this is the second time you're running it, I bet. Because this has to be saved somewhere. Estimates are this function. And then you say, yeah, okay, so this is where you save it. And then you should. So, this is some kind of dictionary. I'm not too familiar with NumPy, so maybe I'm reading this wrong. Estimate influence. Where'd it go? There it is. Okay, 2,000 runs. This is something like T in their pseudocode. Not you. Subset ratio is 0.7. Okay, so this is M. No, this is yeah, I know what they're talking about here. Results is an empty list for I. So this is K. For K, N runs. N runs is 2. Okay, wait. Oh, T. This is T. Yeah. Subset ratio. Results depend subset train. Okay, so what is subset train? Subset train here. Some kind of random number generator. We can just ignore this probably. Step size is 0.1, epochs is 10. 128. Huh. So this, I bet it's some kind of JAX thing. I don't know anything about JAX. But number of training examples. So this is 50,000. Oh, so this is 0.7 times 50,000 integer. Number of batches is this over batch size. Okay, so they're just batching it. So it's a mini batch of this subset here. Here's a random number generator. Do you even... I want to make sure they don't set the seed here. Sorry. Estimate. So it's I run. Okay, they're not doing anything anything weird. This is just something that goes from 0 to n runs. Subset index is it's a choice of the, I'm guessing it's like range of num train total. So you choose these many from, wait, replace equals false. You choose, wait, subset, well, let's just keep reading. Train images is here, train labels is there. Here's a def inside a def. Data stream. Batch. Okay, so it's their, like, they rolled their own data loader. And they shuffled it too. Right? Yeah, okay. Batches. Momentum optimizer. What is this optimizer thing? Optimizers. Oh, it's a JAX thing. Here's this def is also inside this def, huh? Shit, this thing. Update. So this is probably SGD. Stochastic gradient descent. Init params. Here's init the optimizer. Iter tools count, huh? I don't know what count is. For epoch. No epochs. They said it was 10. Train the model. So I'm guessing this epochs is here. For, okay, so this is a iterating through the batches, SGD, params, you get the parameters, and then you measure the batch correctness. I have an idea of what this could be. Well, let's look at the rest of this. Train set mask is initialized as zeros. Train set mask. Subset index is true. So here's a mask. Let's look for batch correctness. Batch correctness. Target class is JNP argmax. Target predicted class is okay, so this is the sum. No? This is the correct labels. Or the correct predictions. Oh, this guy's using NumPy for this, for example, for some reason. Why doesn't he use TensorFlow? Since he works for Google. Wait. Who wrote this? It's this guy. He's the Googler. Anyway, so now we got some results. Results is a list of tuples. List of tuple of the indices. So it's like the indices in the subset. Those that were correct, the correct train predictions, the correct test predictions. Okay. V stack, the first one for okay. Not the train set. What are you doing with this? Correct is okay, so this is like you're gathering all your results into 3 tensors. Now you print the mean test set correctness. More defs inside defs. Masked average. The sum of x times mask. So x, maybe a data set. Scooch over a little bit. I'm assuming this is kind of some kind of accuracy. Masked dot. Well, let's see how they're used. Okay, so this is train set correctness. So these are the ones that you got right. The ones that you got right times the mask. Ah, I see. So this part is something like this, but you're avoiding the loops. Yeah. Yeah, very good. Yeah, so this is the accuracy here. And then you return some dict, memorization, is this influences that? Okay, it looks like everything checks out. Okay. Yeah, so that did not take too long. This is potentially useful. Yeah, I think I'm done here. So yeah. I'm gonna end this stream. There's some new stuff going on with this channel. It's very so maybe now I'm gonna talk about me a little bit. It's very unlikely that you know who I am because this kind of activity is very different from stuff I've been known for on the internet. So anybody who finds this video is unlikely to recognize me. This little guy on the bottom right here, I'm still working on him. I don't know what's gonna happen. If you have any ideas on like what to name him, maybe some background story, let me know. Otherwise, I'm just gonna make some stuff up. Okay, so till next time, maybe I'll read another paper. Maybe I'll just do more studying because I'm actually a grad student. So maybe we'll see more boring studying with stuff blurred out. I don't know. I'm not really trying to build this channel up. Okay, we're done.